the frame structure, we have a staircase in between two floors. If they are well designed separately, like targeted staircase kind of thing in a separate frame, there is no issue. But invariably, sometimes they try to connect to the existing column, especially open column, and then connect to the floor the way that you are seeing in this picture. Obviously, the way in which you are connecting is going to change the behavior of a column, as I told you, short column effect kind of thing. And in addition to that, how that joint is detailed is also an issue. So suddenly, if you do connect like this, so the failure will be only at that point. So that is the issue here that you can see here. So the staircase interacts with the frame, and then during lateral forces, and they get affected. And we have seen weak story and stiffness irregularity in the previous case also. So these are the pictures in which we call pancaking. The whole big structure comes down with um, what we call weak story. That is, the columns are not having enough strength to resist, even though it is regular or what not regular as the case may be. Stiffness irregularity is one when we have soft story kind of thing, or variation in the elevation, something like that. Even if you have a regular building, if you have a weak story, that means the columns are not that strong compared to the beam. So that situation also can create pancaking. This kind of pancaking means one slab above the other. So this is a pancaking failure. Suppose ground floor slab, first floor slab, second floor slab, third floor, and all slabs are one over another. So that means all the column failed. In a soft story, only ground floor fails. But in a weak story, everything fails. All columns fail, the whole building also fails. And the way in which they design is a serious problem in those cases. Next, we would like to discuss about column flexural failure. If you know if you know the normal bending moment distribution in any column is the maximum bending moment will be top or bottom. That is the way it is. In between, it will be reducing, and some point maybe there is no bending moment, zero bending moment will be there. So this is a normal bending moment diagram of any column. So this is under normal dead load and dive load situation. But when lateral load comes, again there is an additional bending moment due to earthquake, which is also similar to the same case like maximum bending moment at the top and similar maximum bending moment at the bottom, and in between it is varying to zero in between. So that obviously brings us to a point where the bending moment is going to be maximum at this point, top of the column. So the top of the column is likely to fail. So this is what is called flexural failure. Flexural failure. So you are able to see that. You are able to see here also. So this is a column, especially when it is not supported with any wall in between. This is another crushing. All these photos are taken at Bhuj region only. So if there is a wall, there is a support system, but here there is no wall here. So obviously the maximum bending moment will be at this point, it will crush. So it is a natural thing to happen. Uh, of course, it depends. Some maximum bending moment can be at the top or it can be at the bottom also, mostly in the top. So either the top crushes or bottom crushes. So in this case, the top crushed, showing that the maximum bending moment came at that point. And these are all the other pictures that is taken in Manipur and the Imphal earthquake. Very similar. Initiation is due to top bending moment. Of course, for various reasons, it continues. Not like the previous cases. Here it continues up to middle. So this can be, it all depends on what is the bending moment that is coming, what is the reinforcement that you have given, all that. So another issue is, assuming that your beams and columns are nice, the issue is in the joint. How do you design the joint? How you detail the joint? That is also a problem. So because of the weak detailing of the joint, so you see all the joints only fail. As the column is withstanding, but this joint only fails. So this is another. This is also joint only failing. The column is fully intact because of the beam and column joint only failed, so it sheared away. Lateral force, it takes away the column column in the same position, but beam is taken away of that size. This is what is called beam column joint failure. Beam column joint actually, let me say a column is well designed and the beam is well designed, whatever. So the joint should be designed for its diagonal shear, whatever, or at least you should have a confinement reinforcement as given in 3920. So otherwise, this kind of situation will be there. So that is a serious problem that one has to take care, either in the design or in the detailing issue. This has happened in bridges also. In bridges, in addition to this frame failure is mostly happens because of the bending moment that is exceeding the top or bottom. So that is one case that is clear. So that means in the frame system, it is very clear that either top of the column failure or bottom of the column failure. But in a pier, RC pier that is supporting a bridge or whatever, shear failure is predominant. So there is a premature shear failure in the RC pier. I will explain a little later about that. So this is a shear failure that happened as you can see here. So all the cover gone and then main rivets would also flexed and this is a serious problem. This is another insufficient. This is not in from India. Okay, the previous this picture is okay. This picture is taken from outside India. So insufficient confinement. They say that the question is because of the heavy shear that is there. There are only two possibilities. Either the section is not sufficient. That is one possibility. One has to check that and then increase the section. Or the other possibility is as per 3920 we need to have confinement reinforcement. So the shear spacing should be 150 or something like that. But since they are not given like that, that fails. If only they had this confinement in all these places, either in the previous case here also. If there were confinement in this case, that is shear reinforcement at a lesser spacing than what is given, it would have saved that failure. So this also like same thing. So here this also another shear failure. This also another shear failure. So one can see that in a pier system, because it is something like cantilever from the ground, so the bottom bending moment issue is less, but the shear issue is very high. As I told you, it is roughly 12 by L cube into delta. So the delta is a deformation that is going to be experienced at the top of the structural system. So during an earthquake, it is going to happen. That is the way it is. So depending upon Tole Bay and delta, that the shear force is going to be lateral force or shear force as the case may be is not sufficient to take care of this failure. So one has to take care of this kind of shear failure. So most of the failures are only in the shear, not like a frame system where we bending moment failure. In a pier system, shear failure. So this is also column failure, shear failure. Because bending moment means top and bottom would have gone. Here also top and bottom is intact, but the center, this is mainly due to shear issues. So generally, but here also premature shear failure at the column. Here also, of course, here plastic hinge formed. Yeah, because there is some kind of frame action started, and then plastic hinge formation. Plastic hinge formation at the bottom happened mainly because of the higher bending amount that has happened. So that is the way we have to understand this. Um, and this is a shear failure of a pier because of the short column. As I told you, if the column is less in length, the shear force is going to be larger in real life. That is the way it is. So that is why you have a full shear this thing. And assuming that there is going to be shear failure going to happen, so you try to increase the uh, size of the column or pier at the top. That means you are shifting the failure zone somewhere here. That is the way it is. So that means it has not failed at the top due to anything, but you are creating a zone of failure here, which is again a shear failure. So this is even though theoretically it looks like everything is fine, you are increasing the size at the top, so you are much better for the bending moment diagram and shear force diagram. That is the way we think. But we have issues like this, which where we fail. We see the initiation at this point and this failure at this point, and then further failure in the further failure. These are all real life cases, how slowly, progressively they failed, and then it end up here saying that they kind of shear fail. So that means by increasing the size of the top pier, we are not able to achieve anything. Instead, we failed by shear at this point, shifted the point of failure to this point purposely. So same is the case here, fifth failure, sixth failure. So that means sequentially how it failed. This for the same column how it failed. This is only for you to show this. So but the buckling of reinforcement, once it fails in shear, the reinforcement only will buckle because there is no vertical resistance because the concrete crushed. The reinforcement cannot take that kind of bending moment there. So buckling of reinforcement in the piers is another possibility at the top bottom failure. This is a buckling of long bars caused by bad confinement. So in all these cases, what are we really missing is spacing. So let us see how these Japanese guys have done this issue. For example, premature shear failure of reinforced concrete piers resulting from insufficient development length happens. So the common design practice prior to 1985 in Japan, this is taken from Japanese code. So they what they decide was they did was, so they decide for the vertical reinforcement, main reinforcement as required, and the shear stirrup they got 300 mm. because in frame we have D by 4, but here this big pillar will be 1 meter and above, no, pier. So there will be D by 4. If you put, it will be 300 or 400, 500 like that. So anyhow, they want to restrict, so they said 300 is the spacing. But after seeing this many failures that I have shown in the previous slide, so they have changed this into 150 So this is what is enhancement of ductility capacity. So the only way is, even Japanese have done prior to 80 like this. After 95 Kobe earthquake, they changed their area. So what is changed between the old code and new code of Japanese is only the shear stirrup spacing is changed. So this is what is called confinement. A confinement is nothing but this in reinforced concrete also they talk about D by 4. That is, if the depth of the beam is 300, the spacing of stirrup should be 300 by 4, that is 17 mm, like that. So R 400 mm means 400 by 4, it is 100 mm spacing. So the spacing of the shear stirrup is Z. Accordingly, this confinement is improved and the ductility is improved and the failure is avoided. So this is the only way that we can come out of this kind of failure.